Welcome to Maths with EJD. I'm talking about contraction maps and applications, still in the real analysis playlist. So, contraction maps and applications, we have some core ideas that'll give us a fast overview on this topic. So first of all, we are beginning to get into the concept of metric space. Well, if necessary, sometime in the future, I might talk about metric spaces like that, if necessary. Okay, so metric space overview, a kind of preview, right? In metric space, having a set X and the distance measure D is complete if every Cauchy sequence converges to a point of X, right? So every Cauchy sequence in it converges to a point inside of X. And then we have contraction. So we're talking about contraction maps and applications, right? So in order to define a contraction, that is how we have to define the idea of metric. So for a contraction, we can say that a map T, which maps X to X, is a contraction. So it maps an element inside of X to another element inside of X. We say it is a contraction if there exists a particular K in the half open interval 0, 1, such that the distance between tx and ty is less than or equal to k times k times the distance between x and y for every x and y belonging to x. So that is the idea of a contraction. So if you have t which maps x to x, and then you now have a particular k belonging to the half open interval, such that the distance between tx and ty is less than or equal to k times the distance between x and y for every x and y in x, then you say you have a contraction. And then that leads us to the concept of Picard iteration. So given x naught, which belongs to x, then we define xn plus 1, which is t of xn, right? T of x sub n. So for contractions on a complete space, xn, for contractions on a complete space, rather, xn converges to the unique fixed point x star with tx star equals x star. So the idea of fixed point is that f of x is equal to x. So the x star satisfies the fact that f of x equals x is what you can call a fixed point. So let's move ahead and talk about definitions, intuition, and quick diagnostics as far as contraction maps and applications are concerned. So we talk about contractions versus Lipschitz maps. A contraction is a special case of a Lipschitz map with constant k less than 1. So if x is equal to r is n-dimensional, it exists in a real n-dimensional real number system with this norm, and t is differentiable, a practical test is that the supremum of x belonging to d for the norm of dt of x, right, less than or equal to k less than or equal to 1, implies that t is a contraction on D. T is a contraction on D. And then we have self-map plus shrinkage condition. To apply Banach's theorem, we can check for self-map, where T of D is an improper subset of D for a domain D which belongs to X. Then we have shrinkage, that the distance between Tx and Ty is less than or equal to k times d of x comma y, the distance between x and y, right? With some k less than 1, right? So completeness then means that D must be complete, e.g. a closed subset of a complete space. And then that takes us to Banach Fixed-Point Theorem. So we have the statement, proof, and error bounds. So first of all, we have this that, so first of all, we have the Banach theorem, which states that, given that let x, comma d be a complete metric space and T maps x to x, a contraction with constant k, which belongs to the half closed half open interval 0, 1. Then we have the existence and uniqueness. So there's a unique fixed point x star which belongs to x with t x star equals x star. We saw that before. Then for Picard convergence, for any x not belonging to x, the sequence xn plus 1 equals t into xn. X sub n converges to x star, that fixed point. Then we have a priori error. So a priori error is d. You have d, the distance between xn and x star. That's d of xn comma x star is less than or equal to k raised power n over 1 minus kd into x1 minus x. And that's the distance between x1 and x0. Then you also have a posteriori error, which tells us that the distance between x1 and x star all right, is less than or equal to k over 1 minus k into multiplied by d into xn minus, comma, xn minus 1. Okay? Then we have the proof in the real number line on the closed interval AB with the geometric. So for instance, well, let xn plus 1 be t of xn. Then we say that the absolute value of xn minus 1 minus xn is equal to the absolute value of t of xn minus t of xn minus 1, and that is less than or equal to k times the absolute value of xn minus 1. And by induction, we say that the absolute value of xn minus 1 minus xn is less than or equal to k raised to power n into absolute value of x1 minus x naught, right? Hence, for m greater than n, we can say that the absolute value of xm minus xn is less than or equal to summation from j equals n to m minus 1, but the absolute value of x j plus 1 minus xj less than or equal to summation from j equals n to infinity of k raised by j into x1 minus x naught equals k raised by n over 1 minus k into x1 minus x naught. Thus, we can say that the sequence, the xn sequence xn is Cauchy, so it converges to some x star because the closed set AB is complete. And we have continuity of t, which is implied by Lipschitz, gives that x star is equal to t of x star, being a fixed point. So uniqueness then, if tx is equal to x and ty is equal to y, then absolute value of x minus y is equal to absolute value of tx minus ty less than or equal to k multiplied by the absolute value of x minus y, which implies that 1 minus k into absolute value of x minus y is less than or equal to 0. And that implies that x is equal to y. The error bounds follow from the inequalities above. So we have a remark there. So the same proof holds in any complete metric space. So if you have any complete metric space at all, so all you just need to do is to replace the absolute values with d of whatever metric space you're dealing with, right? So we have a worked example here. We have example a simple scalar contraction on an interval. So let t of x be equal to x plus 1 over 3 on the closed interval 0, 1. So that means that function is only defined on that closed interval 0, 1. So we have a self map. So for t of 0, 1, right, what happens here is if you put 0 for x, you have 1 over 3. If you put 1 for x, you have 2 over 3. And that's a subset. I mean, 1 over 3, 2 over 3 lies completely between within the closed interval 0, 1. That's the self map. Then what about the contraction? The contraction is such that the absolute value of t prime of x, when you differentiate this now, of course, you're going to get this is like okay. So if you differentiate this, 1 over 3 is outside, differentiate x plus 1, you get x. You get 1. So that's why you have 1 over 3. And 1 over 3 is less than 1. That implies that the absolute value of t of x minus t of y is less than or equal to 1 over 3 into the absolute value of x comma y. That's what this implies. And then we have the fixed point. The fixed point is the value of x which satisfies that the function is equal to x. So for fixed point, we are saying that t of x is equal to x. That means that x is equal to x plus 1 over 3. And if you do that, 3 times x is 3x, and you have 3x equals x plus 1. Okay, so if you collect like terms, so you have 3x minus x equals 1. That's 2x equals 1. Meaning that if you divide both sides by 2, you now have the fixed point x star is equal to 1 over 2. So at that fixed point now, so it means the value of x star is the value of that function itself, because f of t of x star is equal to x star. That based on this, now we now have the Picard iteration from any x naught belonging to the closed interval 0, 1. We can say that x approaches half with geometric rate k, which is equal to 1 over 3 right here, right? That's the Picard iteration right there. Okay, so you can see we are getting the idea of Picard iteration from fixed point and from contraction, right? So we have another example, example 2. We have a nonlinear situation where x is equal to cos x, still on the closed interval 0, 1. So what do? Let x be equal to cos x, right? Let t of x be equal to cos x. And the domain of definition is the closed interval 0, 1. So for self map, you have cos 0, 1. So if you put 0, right? Put 0, you have cos 1. So you have that. If you, no, if you put uh, okay. If you put one, you have cos one. If you put zero, you have one. Now, the reason why cos one is coming first, you can already imagine that, cos is bound between minus one and one. Okay. So if you put zero, you get one, and that's the highest it can be. And if you put one, it's some value, small value, 0 point something. So and that's why cos one is coming first. And you can see that it's the total subset of the interval of the domain of definition, 0, comma 1. Now, if you talk about the contraction now, what do we do here? Take the absolute value of the derivative. So the derivative of cos x is sin x. So the absolute value of sin x, of course, will always be less than sin 1, which is less than 1 itself, because sin 1 is some very small 0 0.0 something, right? So sin 1 is less than 1 on the closed interval 0, comma 1. So k here will be something like sin 1, which is approximately 0 0.84, all right? So there we got our K. And then for the conclusion, now we go for the unique fixed point X star will be something like, you're trying to say you have cos X is equal to X. So if you want, so you can only solve that numerically because you can't factorize. So it's more like you have like X minus X, X minus cos X equals 0, or cos X minus X equals 0. Anyhow you like that. So, and that can be done numerically. So unique fixed point X star in the closed interval 0, comma 1 that satisfies that cos x is equal to x is something roughly like 0.739085. So iteration xn plus 1 will give us cos xn, which converges to x star for any x naught belonging to 0, comma 1 like that. And then we have example 3. For example 3, we have okay, it's the same way. Example 3, you have vector case via Jacobian bound. So in the n-dimensional real number line with the Euclidean norm, suppose T is once differentiable. I believe that's what C1 means. On a convex set D, and the supremum as x for x belonging to D of the absolute value of D times T of x is less than or equal to the supremum of the norm rather is less than or equal to K less than 1. Then we can say T is a contraction on D. So by Banach's theorem, T has a unique fixed point in D, and Picard iteration converges to that unique fixed point, right? So we'll move on to Picard iteration for ODEs. This which gives us a preview of the Picard Lindelöf. Okay. So okay, well, I guess I want to expand this. Then when I come down here, I'll just do that. Okay. Consider the initial value problem y prime of t, which is equal to f of t, comma y of t, and comma yt of 0 equals y naught. So let's see. So if you now do, is this like some self contraction? C of t naught plus h, m-dimensional real number, be the space with the supremum norm. So the norm to infinity of y is supremum of t belonging to t naught, comma t naught plus h, for absolute value, for the norm of y of t rather, which is a complete metric space. So we define the Picard operator. So here we talk about the Picard operator. Ty of t is equal to y naught plus integral from t naught to t, f of s, comma y of s ds. So if f is continuous rather, and Lipschitz in y with constant L on a rectangular around t naught, comma y naught, then for yz, the norm of ty minus tz to infinity is less than or equal to the sup of t belonging to t naught, comma t naught plus h closed interval integral t naught to h, to t of L of the norm of y of s minus z of s ds, and that is less than or equal to LH, the norm of y minus z to infinity like that. And then we choose, so we have to choose h greater than 0 so that LH is less than 1, then T is a contraction on a suitable closed subset of C of T naught, comma T naught, comma plus H, m-dimensional real number. Hence, a unique local solution exists, and the Picard test yn plus 1 is equal to Tyn converge uniformly to that unique local solution which exists. And then we come to the idea of Newton's method as a local contraction. Okay. I mean, you discover that as we've been talking about contraction, right? Contraction talks about, taking the norm of derivative and things like that. So we've seen previously. So we have a setup and statement. So let f belong to twice differentiable sets on the closed interval AB with a simple root psi which belongs to the open interval A comma B. That is, f of psi is equal to 0, whereas f prime of psi is not equal to 0. So define the Newton map. I mean, this is what sometimes it is also called the Newton-Raphson method. So you have n of x equals x minus f of x over f prime of x. So if you can find a small closed interval I, which is psi minus rho comma rho plus psi plus rho, which belongs to the closed interval AB, such that f prime of x is bounded away from 0 on I. Okay, so we now have the infimum of x belonging to I for the absolute value of f prime of x greater than or equal to m greater than 0. And then we have f prime prime is bounded on I. And we have sup of x belonging to I. Then absolute value of f prime of x less than or equal to m, like that. So that's some kind of boundedness. And then you have n of I less belonging to I, which is a self map. Then n is a contraction in that case. So we say n is a contraction on I, provided the sup of x in I for absolute value of n prime of x is less than or equal to m over 2m, diam I less than 1. In fact, um, in fact, we say that n prime of x is equal to f of x, f prime of x over f prime of x all squared near a simple root. Absolute value of f of x is approximately less than or approximately the absolute value of x minus I sup of absolute value of f prime, which makes the absolute value of n prime of x small on a sufficiently small I. In conclusion, for x not belonging to I now, the iteration xn plus 1 is equal to n of x sub n converges to psi. So a stronger conclusion will be, once close enough, convergence is quadratic. Contraction guarantees at least linear convergence and uniqueness in I. So we have a practical contraction box recipe, right? So pick an initial guess x naught with f prime of x naught not equal to 0. Then choose a small radius rule so that on I, which is equal to closed interval x naught minus rho, x naught plus rho, m is less than or equal to the absolute value of f prime, and big M is greater than or equal to absolute value of f prime prime, then n of I is contained in I, so you can check the point. Then you have k, which is defined as the sup for x belonging to I for absolute value of n prime of x is less than 1. Then you can apply Banach. So unique root in I, Newton iterates stay in I and converge to psi, like that. Then you have error control and stopping rules. Okay. So for error controls and stopping rules, so anytime you have iteration like that, you need a stopping rule, right? Well, you need to know when to stop. So for a contraction T with constant k, a posteriori bound stop when the distance between xn and xn minus 1 is less than or equal to epsilon into 1 minus k over k, to guarantee that the distance between xn and x star is less than or equal to epsilon, like that. Okay. So, and then we have an iteration budget. We have an iteration budget which says that from the distance of x1 to x0, we need n such that k raised by n over 1 minus k d of the distance between x and x1 comma x0 is less than or equal to epsilon. Equivalently, n now is greater than or equal to the log of epsilon, into 1 minus k over d into x1, x0, all over log k. So we'll talk about applications at a glance. The topic is contraction maps and applications, right? So what are some applications of contraction maps? That's one of the reasons for this video. So talking about the applications now, we have algebraic fixed points. So you can solve x equals t of x by designing a contraction t, e.g. rearrangement of equations and damped iterations. Then you have nonlinear systems. In the n-dimensional real number system, ensure that the supremum of the absolute value of the norm rather of dt is less than 1 on a closed invariant set. Okay. Then you have ODEs, where you talk about Picard, Lindelöf. So you have local well-posedness when f is Lipschitz in Y, and then for PDEs and integral equations, contraction arguments on appropriate Banach spaces with norms tuned to gain a small factor, e.g. via small time h or small data. So And then we have problem sets with hints and solution sketches. Right. So warm-up contraction. Okay, I think we've dealt with this before. Prove that T of x equals x plus 1 over 3 is a contraction on 0, 1, and find its unique fixed point. So the hint is you want the absolute value T prime, which is 1 over 3. Of course, if you differentiate this and you take absolute value, you get 1 over 3. Therefore, the fixed point, you just say x plus 1 over 3 equals x. And when we did that before, we got fixed points x starts to be 1 over 2, and the rate is k, which is 1 over 3, like that. So that's the warm-up. And then we move on to the cosine fixed point, okay, which we could only get the other time numerically because we can't get a closed form solution for that, sort of. So show that T of x equals cos x is a contraction on 0, 1. Conclude existence and uniqueness and convergence of xn plus 1 equals cos xn. Hint, absolute value of sine nx, that's the derivative of cos x now. Absolute value of sine x, rather, which is the derivative of cos x, is actually less than or equal to sine 1 and less than 1, which is less than 1. So self-map holds since the cosine of 0, 1 belongs totally to 0, 1. Because if you take cos 1, you get 0. If you take cos 0, you get cos 1, which lies between 0 and 1. So in that case, now we can say self-map holds like that. Okay? Then we design a contraction scaling trick. So if imagine that for g of x equals x cubed plus 3x plus 1, define tx equals x minus alpha g of x. Then you find alpha greater than 0 and an interval I, so that t is a contraction on I. So the hint is you want to control the supremum for x belonging to I, so that the absolute value of t prime of x is equal to sup of absolute value of 1 minus alpha g prime of x, like that. So that's the hint for you right there. Okay, so choose I where G prime stays in the closed interval M, small m, comma big M, and pick alpha belonging to 0, 2 over M plus M. So if you follow this, you get the results you need. Those hints are helpful. Then Newton local contraction. Let f of x be equal to x squared minus 2. So you want to show that the Newton map n of x equals half into x plus 2 over x. I mean, you know, that's some kind of derivation or something like that. So is a contraction on an interval I equals closed interval root 2 minus rho, comma root 2 plus rho for small enough rho. So hence compute n prime of x. So differentiate this for sure, and then you get 2 over x squared minus half, and then show that absolute value of n prime of x is less than 1 on small I around root 2, and check that n of I is a subset of I. All right. It's a subset or equal to I itself, in fact. So then you have Picard for a simple ODE now. Okay. So consider y prime equals y. That's just dy dx equals y straight. Easy. So y of 0 is equal to 1 on the closed interval 0, comma h. Show the Picard operator t y of t equals 1 plus integral from 0 to t y of s ds is a contraction in c of 0 h with norm to infinity for h less than 1. So the hint is the norm of ty minus tz infinity is less than h norm of y minus z infinity. So conclude the existence, uniqueness, and that the limit is e raised power t, like that. Then you have the a posteriori stopping test. Suppose k is 0.5 and the absolute value of xn minus 1 is equal to 10 raised power minus 4. Then bound absolute value of xn minus x star. The answer is simply this, that absolute value of xn minus x star is less than or equal to k over 1 minus k. Absolute value of xn minus 1 equals 10 raised power minus 4, like that. I think we've done something close to that previously. Then we have some common pitfalls, as usual, and some best practices. Forgetting completeness. So Banach fails without completeness. If there's no completeness, there's no Banach. So Banach fails without completeness because a sequence may be Cauchy but not converge in D, right? So you need completeness to be able to progress with Banach. Not checking that T of D is a subset of or is equal to D. So even with k less than 1, if iterates leave the domain, the argument breaks. Okay? Then you have the derivative test misuse. Condition SOAP of the norm of dt less than 1 is sufficient but not necessary. If it slightly exceeds 1, try shrinking the domain or changing the norm. That is preconditioning right there. I mean, I can't think about this in even in machine learning where you have to do some parameter tuning or something like that. I'm seeing a bit of similarity with that right now. So Newton's method, far from the root, it may diverge if the starting point is too far. Okay. So if you're using Newton's method, your initial guess should be something pretty close to the root or what you can call the zero of any expression you're working with. So you need to build a contraction box to guarantee convergence and uniqueness. Okay, so we have some mini checklist when applying Banach. First of all, like we said, Banach operates with completeness and closedness too. So the first thing you want to check is the working set D closed and complete? If it's closed and not complete, no way. If it's complete and not closed, no way. It can even be complete without being closed. So, I mean, closedness and completeness must be met. Then, do I have T of D to be a subset of D or even equal to D? Second thing to check. Then, number three, can I bound the contraction constant K to be less than 1? Check. Do I want a priori or posteriori error guarantees? Then for ODEs, can I make the time window H small so that LH is less than 1? Then if all of that is done, then you're set. Then you can just begin to iterate. You just have xn plus 1 equals T of x sub n, and then monitor the absolute value between xn minus xn minus 1, because this will be your stopping criteria. And in that case, you can enjoy guaranteed convergence. So with this, we come to the end of this video about contraction maps and applications. Talking about Banach, we had to talk about metric space, Banach space, and things like that. But in real analysis, right, you at some point you begin to talk about metric spaces. Although metric spaces are separate topics on their own, which we may talk about in the future if a need arises for that. So with this, I come to the end of this interesting video about contraction maps and applications. If there's something you'd like me to try out, feel free to let me know. And let me know how helpful this is for you. If you have subscribed already, I must say thank you. If you haven't subscribed, of course, it's only commonsensical for you to subscribe. So just go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can click on join also to become a member of this channel. And that comes with some special privileges like having one-on-one hangouts, or if you can also get PDF documents of my maths teachings, and all that. All right. So you want to do that. And ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here till I come your way again. Keep doing maths right. Bye.